Welcome back to eCoreAcademy, everyone. My name is Anita Raj, and I am one of the teachers and co-founders here. As you can see, today we're going to be doing a new Biology 1 lesson. If you haven't seen my previous videos, they'll be linked in the description box below, but you can see my very first video where we're introducing you to the new Biology 1 curriculum eCoreAcademy is offering, and you'll see the second one, which is the first part of this mini-series I'm making. So we're pretty much going to be going over the process of science. In the process of science, I'm mainly talking about the scientific method, which I'll be showing you on the next slide, and how we can use that method to design an experiment, which is specifically what this video is on. In the first video, I talked about what the scientific method is and different components of it, such as words that are going to come up when you go through the scientific method and you design your experiment, such as variables, such as inferences and hypotheses. Just things like that. So when I use those words in lessons like today, where I'm talking about how you design an experiment, you'll know exactly what I'm talking about. So today, again, we're going to be incorporating components of the scientific method that we learned about in our last video. And today we're going to actually design a new experiment using what we've learned. So before I even begin this lesson, I would really appreciate it if you took the time to pause, like this video, hit the subscribe button, hit the post notification bell, drop a comment down below, and share it using your socials. You can find a bunch of links to our social media platforms in the description box as well. Now let's get right into the lesson. First, I want to do a review of the scientific method. And as you can see, I have no real notes up on the screen because I want to keep it super simple. Again, this is just a review. Instead, I have a flowchart that I found on the internet, very good depiction of what the scientific method is. So first, let's just go right through this flowchart, and I'll just cover things and explain things as we go through it. So we have asking a question. What you're going to do first is you're going to observe a situation. So you might, like we said before, discovery science and hypothesis-based science go hand in hand because at the end of the day, science is a way for humans to reason for what goes around in the world around us. We use science to reason for natural phenomena and just occurrences in nature that we can't explain. That back then, in the medieval times, even before the Enlightenment and Renaissance, we used to reason for those things with religion. But now using science, we can try to reason for those things using theory and just laws that we understand. So whenever we're trying to understand a situation, we use a scientific method. And first off, to pique that curiosity, as in to get this whole experiment going, we have to observe our environment and we have to pick out something that stands out to us. So first we want to make observations. Just pretend that's included up here. So first we want to make about a subject. Afterwards, after seeing those observations, we want to ask ourselves a question. So I'll come up with a quick example. So let's say we have a brand of sugar. Let's say we're making artificial sweeteners and we're giving them out to the public. And as a scientist that's working for the company, I'm getting messages and I'm getting notifications that a lot of people who are using the artificial sweetener that my company is making, I'm getting news that a lot of them are getting kidney cancer and kidney-related diseases. So I'm making observations. So when I hear this news that people are getting kidney cancer and these people are also users of our artificial sweetener, I might start making observations, as in I might collect a few people who have kidney cancer so I can do studies and understand what is the correlation between the artificial sweetener my company's developed and these people, our consumers, getting kidney cancer. So that could be like your observation. You're observing what's happening to the population. Then you're going to ask a question. So it's included up here. You're going to be asking a question, as in you're going to be trying to develop a question that you can base your whole experiment off of. So you're going to ask yourself a question. What is the correlation between kidney cancer and my company's artificial sweetener? So you might ask yourself a question like that. Whenever you ask yourself a question, there's a way that you can find an answer. So you have to ask yourself a question to which you can do research and experimentation to find an answer. So next, even before you develop your hypothesis, you are going to do some background research. So you're going to take, you might look at the artificial sweetener that your company's developed, and you might look at the ingredients that go into developing that artificial sweetener. You just need to understand the situation before you start trying to design an experiment off of it. After you do your background research, you're going to construct a hypothesis. So you're going to construct a hypothesis such as, if people consume the artificial sweetener, then they will or will not get kidney cancer. So you're going to try to develop an if-then statement that describes the situation. So your first part would be something like, if people consume the artificial sweetener, that could be your first part. And then your second part is mainly developed off of the opinion you formed based off of your research. So maybe your research has led you to believe that this artificial sweetener is totally healthy and does not cause kidney cancer. Then your then statement would be, if people consume artificial sweetener, then people will not get kidney cancer. They should not be getting kidney cancer. You can be like, there is no correlation between kidney cancer and the artificial sweetener. After you construct your hypothesis, you need to develop an experiment around it. So just like how you did research based off of your question, you're going to experiment based off of your hypothesis. So you're going to be testing it with an experiment, and on the next slide, I'll be showing you exactly how to design an experiment, which is the topic of this video. So you're going to test it with an experiment. After you conduct that experiment, you're going to have experimental groups. You're going to have one control group. You're going to have your independent variable, the variable you're manipulating. Maybe in this case, your independent variable is going to be the amount of artificial sweet. Maybe you'll have 4 experimental groups. I'm just making this up in this artificial sweetener situation. Maybe your first one will be your control group, so you're not giving any artificial sweetener to them. Maybe your first group, you're giving about 10% concentration artificial sweetener to them. Maybe your second experimental group, you're giving 20% artificial sweetener to them. And then maybe for your third experimental group, you're giving 40% concentration artificial sweetener to them. So the experimental factor, and again, if you don't really understand what I'm saying with control group and experimental group, that's totally fine. I'm going to go through that in this presentation. So then you administer your experimental factor, you observe, and then afterwards you will collect your results and then analyze these results. And by analyzing especially the quantitative data, you're going to be able to draw a conclusion. And your conclusion is always going to tell you if your hypothesis is true. So if it's true that you find no correlation between your artificial sweetener and kidney cancer, then your hypothesis was true. However, if you do find a very strong correlation between kidney cancer and your artificial sweetener, as in the artificial sweetener is causing the kidney cancer, then your hypothesis is false, or maybe it's kind of true. It totally depends on the nature of your hypothesis. No matter what, if your hypothesis is true or if it's false, you have to report your results. So you can share your results with other scientists, because you don't want to have any bias. You don't want to redo this experiment when you know what the results are, when you know that your hypothesis was wrong. You just want to report the results to the population of scientists. And then lastly, if you see this little arrow over here that's kind of going off the hypothesis is false or partially true, it says think or try again. So what happens is, after you report your results, even if your hypothesis is false, you're going to try to redo the experiment, and maybe you'll keep the same hypothesis. Maybe you'll alter it a little bit, and then you'll redo the experiment, because you never know. You can have experimental errors. So you want to run as many trials as possible. So you end up getting a large volume of data to analyze in your hypothesis. And when you validate your hypothesis and your conclusion, you have the most data to back it up. So you're going to try to run multiple trials of your experiment. So that's the scientific method with an example that I came up with off the fly. Here exactly is the experimental design process. So I'm going to go back to the last slide real fast. If you see this purple, oval, test with an experiment, that's what we're going to be focusing on in this video, because that is a very big component. Your experiment and how you execute it are going to influence what results you get, and then whether you can determine if your hypothesis is true or false in your conclusion. So that's a very important component. So the experimental design process is what we're talking about, as in the process of designing a very, very good experiment by outlining the procedure, the experimental groups, the control groups, your variables, exactly how you should execute it, and then actually executing it. So here's the experimental design process. First, you want to define the problem, as in you want to ask a question, do some background research, and then form a hypothesis. Then you want to determine your objectives. I would say this falls under your hypothesis. So what exactly are you analyzing? In that last situation, we were analyzing the correlation between artificial sweetener and kidney cancer. So that is our objective. Our objective is to find if there is a correlation between the sweetener and cancer. Then you want to determine responses and factors. So this is pretty much your variables. So you define your independent variables, and you'd also define your dependent variables. There's something we're gonna learn about called constants. They're also variables, but constants are variables that stay the same. So no matter what, you don't change them. The only thing you change is the independent variable, and then the dependent variable will respond in response to that variable. So in this case, our independent variable, as in the manipulated factor, the experimental factor, the thing that we are changing, is the concentration of artificial sweetener that these different groups are going to receive. Then in result, we're going to have the dependent variable, which is going to be the responding variable. So this is whether the health of their kidney. You can think of it that way. So in some way or another, we would measure the health of their kidney. Then we would design the actual experiment, as in we would outline the procedure. We would say administer this much artificial sweetener through this mechanism, wait for this long. We just specified, we'd make parameters for the experiment. Then you'd actually conduct the experiment, so you would give the artificial sweetener to your experimental groups, and afterwards you'd collect data from both your control group and your experimental groups. Afterwards, you want to analyze that data. So you want to see if there's a correlation between having kidney cancer or having impaired kidney function versus how much concentration of artificial sweetener those test subjects received. Then you want to interpret the results. So this is where you're trying to see if your results support your hypothesis. So if the people who received a higher concentration of artificial sweetener do not show any impaired function in their kidneys, then you could say something like, my hypothesis was supported by the large volume of data I collected. However, if you see that the people who received a high concentration of artificial sweetener have very impaired kidney function, then you might have to reconsider and say the results invalidate my hypothesis. Afterwards, you want to verify your predicted results. So you just want to make sure you didn't run into any errors, and make sure your trials all follow the procedure correctly. Make sure that you're drawing the right correlations. Just verifying. So just making sure you did your procedure correctly and your results are correct. Afterwards, if you will have to determine if additional experimentation is required. And this is what we saw on the last slide, where no matter what result you get, no matter if your hypothesis is to be accepted or rejected, you still report the results. But if you want to try the experiment again, you're free to do so. It's encouraged in science. The more trials you run, the more accurate you can possibly be. So you might want to rerun the experiment. Okay, so now is where we're going to be designing an experiment together, so I can walk you through exactly how you can use these steps of both the scientific method and the experimental design process. So here's a sample experiment. Let's take a look at an example of an experiment designed using the scientific method and the experimental design process. So these are the two processes that we just went over. Those diagrams, those flowcharts were really good. So if you're taking notes, I would suggest you go back and actually copy those down. I don't think you should take that long, but I feel like that's the best way to help you structure your thinking. So if you actually, especially when remote school is over, when you get back in the classroom and you end up doing experiments, especially if you're in higher level classes, you can use that structure to be able to execute the experiment in the best way possible, especially if your teacher gives you kind of vague instructions. So I would suggest you copy those down. So again, let's take a look at a sample experiment that I've come up with. So here's the question. Remember, pretend I already made observations. So in this case, we're talking about plant fertilizers and plants. So let's say I'm a farmer, and let's say all of you are farmers. Let's say we're farmers, and on our farm we use plant fertilizer. Let's say on our farm we have all different kinds of plants, but we have an orchard, and in the orchard we grow apple trees. For these apple trees, let's say half of the apples we sell to one supermarket that doesn't ask for organic apples. The other half we sell to a supermarket that does want organic apples without any pesticides, any fertilizers, nothing. They don't want anything. They just want natural apples. So let's say we have different parts of our orchard dedicated to those different supermarkets that we sell these apples to. Let's say one day when we're fertilizing the apple trees we sell to the supermarket that doesn't really care for pesticides or fertilizers, we realize after we harvest the apples that even though the apples that are given by the trees that don't receive any fertilizers, even though they're a bit smaller, the apple trees that we give fertilizers to are a bit more unhealthy. So what I'm trying to say is, let's say after we give those fertilizers, the trees we give the fertilizers to, we give so much fertilizer to those trees that they kind of look unhealthy. But then the trees we don't give fertilizers to, they might not produce as much fruit, but they're in much healthier condition. And this makes us question ourselves. We observe, maybe we weigh the apples, maybe we're just curious. We don't know why this is happening. So our question is plant fertilizer safe at high concentrations? Because pretend we're giving these apple trees that do receive the fertilizer a lot, because apple trees are pretty decent sized trees. So this is what our question is. Is plant fertilizer safe at high concentrations? And I even included a picture of Miracle Grow, which is a basic kind of fertilizer that people use. So here in this blue box, you'll see instructions as to how exactly, based off of this question, we're going to develop an experiment. First, we got to come up with a hypothesis. So we're going to do some background research. Pretend we already did the background research. Pretend we've done background research, and there's research saying that plant fertilizers contain a lot of fertilizer salt. And a high concentration of fertilizer salt can impair plants and can actually cause plant death. So maybe we do some background information, we find out that fact. Then we want to develop a hypothesis based off of our situation and our question and our background research. Afterwards, to actually start the experimental design process, we want to come up with our independent and dependent variables. Afterwards, based off of that, we want to come up with our experimental groups, and we want to come up with one control group. And lastly, we want to actually put the procedure together and design the experiment so that we can execute it. Moving on to the next slide, we're going to look at hypothesis and variables. So here's the inference. Remember inference, where we see a situation and we try to draw a conclusion based off of what we can see. And inferences and hypotheses go hand in hand. So our inference that I've written here is that plant fertilizer causes plant death at high concentrations because plants cannot tolerate large amounts of fertilizer salt. So maybe I did research. Maybe I purposely just looked at some articles. Maybe I dumped some fertilizer. I picked one tree to be my victim, and I dumped a lot of fertilizer. And then I saw that tree just deteriorate over the next few weeks. Maybe I actually looked at the molecular structure of the fertilizer that I was using, and then based off of all those things, based off of especially seeing that tree die, I inferred that plant fertilizer causes plant death because I'm administering it at such high concentrations, and so much fertilizer salt is not good for it. Next, based off of all that I've witnessed, all my observations, I will form a hypothesis. So an if-then statement that pretty much describes what my educated guess at the beginning of the experiment. So what I think the result is going to be. In this case, I'm coming up with a hypothesis. If plant fertilizer is supplied in large concentrations, then it will cause plant death because of what I've seen with based off of what I've seen, because of the detrimental effects fertilizer salt can have on plants. So that's my hypothesis. Afterwards, we got to define the variables. Remember, we have an independent variable and a dependent variable. As you go on, the amount of independent variables and dependent variables might change. Like, I'm taking AP Bio right now. I remember doing an experiment where we had multiple variables. But remember, at the end of the day, it always comes down to you having one base independent variable and one base dependent variable. And I'll explain why it's really important to have one of each. So in this case, our independent variable is going to be the amount of plant fertilizer administered. That's what we can control. We can control how much fertilizer we're giving to these different plants. That's the experimental factor. This whole experiment is based off of, do different concentrations of plant fertilizer impact the plant? Like, will it help the plant thrive? Will it kill the plant? Things like that. So independent variable is what we're manipulating, what we're controlling. In this case, we're controlling how much fertilizer each plant is receiving. Then we have the dependent variable. Remember, the independent variable is what we're manipulating. The dependent variable is the responding variable. So it's going to respond in accordance to the independent variable. Usually it's going to be some kind of quantitative data, because in the world of science, we use quantitative data to support our conclusions, just because it's we consider it more accurate than qualitative data. So in this case, quantitative data, we could use the weight of the fruit, because oftentimes the health of a tree will be based off of how the fruit, like the quality of the fruit it produces. So in this case, maybe we're going to weigh the apple, maybe weigh like 5 apples collected from each tree in each group, and then we'll weigh them, and then depending on that, we can have a measure for the health of the tree. Okay. Now we'll talk about the experimental and control groups. So we already went over this in the last video. Remember, in an experiment, you'll have one control group. The control group is where you keep things constant. You don't give it the experimental factor, and like we said, the experimental factor in this situation is the plant fertilizer. So in this case, the control group, if you come down here, is not going to get any plant fertilizer. So I just wrote control group 0 cups, meaning if we're measuring the amount of fertilizer we're giving, again, I'm making this up. If we're measuring the amount of fertilizer we're administering in cups, the control group would get none, would get 0 cups. This group is going to be treated with none of the experimental factor, meaning it's not going to receive any plant fertilizer, because we're going to treat it as plants that naturally occur in the environment do, because in the environment, just naturally, apple trees do not get man-made fertilizer. So we're going to treat that like a normal apple tree. No fertilizer. And remember, we have one control group. In this case, it's going to be this control group right here, not getting 0 cups of fertilizer. Then we're going to have experimental groups. So you're definitely going to have more than one experimental group. You might have 2 or 3 or so on. Experimental groups, you can honestly have as many as your experiment calls for. In this case, I decided to do 3 experimental groups because I feel like 2 experimental groups is a bit too simple for all of you, so we amped it up to 3. The first experimental group, so first off, the experimental groups are going to be receiving the experimental factor, meaning they're all going to be receiving the plant fertilizer. Remember, the experimental factor is our independent variable. So they're all going to get plant fertilizer, but they're all different. They're different in the fact that each of them are getting different amounts of plant fertilizer. So that's where the differences in the experimental groups are. They all get the experimental factor, but they're all going to get varying degrees of the experimental factor. So in this case, group 1 is only going to get 1 cup of plant fertilizer. Group 2 is going to get 2 cups, and group 3 is going to get 4 cups. I also want you to take into account, I want you to notice how we're just doubling the experimental factor for the next group by the amount of experimental factor the previous group received. So what exactly does this mean? Group 1 received 1 cup of fertilizer. Group 2 received 2 cups. Well, 2 cups is double 1 cup. And if you look here, group 3 has 4 cups. I didn't write 3 cups, I wrote 4 cups because we're doubling group 2's amount of cups they're getting. So 2 times 2 is 4. That's why we get 4 cups for group 3. And usually you'll see this often when you're talking about concentrations. That's why I just wanted to depict it in this experiment. So remember, we have 3 experimental groups. All 3 are getting the experimental factor, but at varying degrees. And then we have the control group getting none of the experimental factor, and we're going to treat it as normally as possible. So we have a basis to compare these experimental groups to. Okay, so let's talk about constants, which I did not talk about in the last video and which are super, super, super important in experiments. So in an experiment, constants are variables that do not change, and they can be measured, but they cannot be altered during the experiment, as opposed to the experimental factor. So let me break this down. In an experiment, we are administering the experimental factor, and then the responding variable, which is our dependent variable, is going to indicate, in this case, the health of the apple trees. However, at the same time, we're going to have other variables as well. And these could include, I'll show you on the next slide, these could include the amount of time we're administering the plant fertilizer. So maybe we do this experiment for 4 weeks, maybe we do it for a month. And we also have other factors like the amount of sunlight all the trees receive. We have how much water the trees receive. Just things like that. The thing is, those would all have to remain constants. And if you think about the word constant is something that does not change. If you see here, I wrote that does not change. So all those 3 factors I just mentioned, they could be variables. The thing is, we must keep them constant so that we know what the result of the experiment is. I'll talk about that in this green box here. So you can measure these variables, like you can measure the amount of water you're giving the trees. You can measure the amount of sunlight the trees receive. You can measure maybe the pH of the soil, but you need to make sure all of these are same throughout. So all of the test subjects are getting the same amount of these constants. And like it says here, they cannot be altered during the experiment. So all of these need to remain the same. So maybe you're giving, I don't know, I'm just making this up, 1 liter of water to one of the apple trees during the experiment. You must give 1 liter of water to all of the trees, because that is a variable that must stay the same. Because that is not our dependent, our variable. Our dependent variable and that is not our independent variable, which is the experimental factor. Independent variable, the only thing that we should be changing in the way that we treat the trees is the amount of fertilizer they receive. I think that's the best way to put it. That's the only thing we should be changing the way we treat the trees. Everything else, water, pH of the soil, sunlight, all of those need to remain constant. And you might be wondering, why is that? Why can't we change another factor? Like, why can't we change the amount of water we also give? So I addressed that down here. What would happen if one of these variables changed in one of the experimental groups? So by this, I mean, what if we changed another constant? What if not only did we change the amount of fertilizer that the trees were receiving, what if we also changed the amount of water they're receiving? Or we also changed the amount of pH, the pH of the soil? So this poses a problem to the whole experimental design. With multiple factors being affected, at the end of the experiment, the scientists would not be able to tell exactly what the independent variable changed. So if we had multiple independent variables, excuse me, if we had multiple independent variables, as in we were changing the pH of the soil, and we were changing the amount of fertilizer, and we were changing the amount of water that's received, and we end up getting and we end up measuring the weight of the apples, and we get a result. But do we know which of these factors ended up giving us that result? Do we know if the pH of the soil affected the health of the trees? Do we know if the amount of water affected the health of the trees? Do we know if the amount of plant fertilizer affected the health of the trees? We wouldn't know at the end of the day. We would not know exactly which independent variable impacted the dependent variable directly. So on the flip side, with two dependent variables, there is not a definite answer as to which variable may have been changed by the outside factors. So again, if we had two dependent variables, this is why we typically measure one dependent variable. If we measure two of them, we can't exactly tell if the independent variable affected one, both, or neither. We always want kind of a one-to-one correlation between them. So I would say keep your dependent variable to 1, keep your independent variable to 1, because you never know if there's other factors influencing them if you throw in multiple independent variables and dependent variables. So that's all about constants, very important for you all to keep in mind. This is the last slide. It's actually the design part of the experiment. If you see, this is the apple tree, if you've never seen an apple tree before. So the details of our experiment. This is what our experiment is going to entail. The organism, as in the test subject, is going to be the apple plants. I just wrote apple plants, but they're really just apple trees. Each group will have 4 apple trees. So again, we have 4 groups. We have the control group. We have the first experimental group, second experimental group, and third experimental group. Each of these groups are going to have 4 apple trees. So in total, we're going to have 16 apple trees. I just want to make it known that when you're doing trials of an experiment, you always want to have more than one test subject. And the more test subjects you have, the more data you can work with. And the more data you have, the more accurate a conclusion you can draw. So 4 apple trees is kind of small. You probably want to go for 10 to 20. I just used 4 for this example. But try to use as many test subjects as you can, because again, that's going to give you the most accurate result. And also, another thing comes with the trials. So you might want to run this experiment multiple times. So you might have your first batch, and it might be your first time doing this experiment. After that experiment, you might want to do this experiment all over again with 16 new apple trees. So you have to ensure the accuracy of your experiment. You might want to increase the amount of test subjects you have. You might also want to increase the amount of trials you conduct. Here are some additional variables. These are what we talked about with the constants. So understand that all other variables must be constants. These include the time, as in how long are we going to be administering the plant fertilizer. We can't be administering the plant fertilizer for 1 week for one group and then 2 weeks for another group. It all needs to be the same. So if we decide on doing administering the plant fertilizer for 1 month for one group, it needs to be 1 month for all of the groups, excluding the control group. Of course, that's not getting any experimental factor. Maybe the temperature. So these plants must all be in the same temperature. So for example, we can't have our friend who's a farmer on the other side of the country doing this experiment with 2 experimental groups, and then I'm doing the same experiment, but I only have 1 experimental group plus the control. Like, we can't split the experiment. And maybe the plants that he has all live in a temperature of, like, I don't know, 60 degrees Fahrenheit, and my plants live in a temperature of 50 degrees Fahrenheit. That can't change. It needs to be the same temperature. Additionally, maybe the pH of the, I don't know why it says soil here, but it should say soil. So the pH of the soil. So you want to maintain the same pH, because the acidity or alkalinity of the soil can also impact the health of the tree. And you wouldn't know if the health of the tree was compromised because of either the amount of plant fertilizer or the pH of the soil. So that becomes unclear. Exposure to sunlight. So all the trees need to be exposed to sunlight for the same amount of time. This will be taken care of if they're all in the same orchard. The amount of water they receive. So all of them should receive the same amount of water from the scientist who's conducting the experiment. And then the last example I said was the same orchard. So this is pretty much the same, synonymous to the same environment. All of these apple trees would benefit if they're all in the same orchard, because they're all in the same environment, and you don't need to worry about different environments impacting the plant growth. So keeping them all in the same orchard is also another constant, and then etc. This includes pretty much everything. So constants are all variables that you consider except the plant fertilizer, which is the experimental factor. So if you can think about anything you can change, anything you can experiment about. You can experiment about the amount of time that the amount of time a plant has to grow, the temperature the plant can grow in. These are all variables. These are all things you can pick to be the experimental variable. However, because you picked the plant fertilizer to be the experimental variable, none of these other ones, they're all off the table. You cannot make any of them also the experimental factor. They all must remain constants for this experiment to work and yield good results. Lastly, we're going to be examining the dependent variable via the weight of the fruit collected from each tree after the experiment ends. So, like I said before, our dependent variable, usually something we can measure, is going to be what is going to respond to the amount of fertilizer we give the plants, and we're going to measure the health of the tree after we administer the plant fertilizer by measuring the weight of the fruit collected from the tree. So usually a unhealthy tree is not going to yield very good fruit. So it's going to probably yield very small fruit, maybe no fruit at all, or underdeveloped fruit. Whereas a healthy tree is going to yield better fruit, riper fruit, crisper fruit. So that's how we can measure the health of the tree. And I am not a scientist who actually conducted this experiment. I'm just trying to give you ideas of a dependent variable you can use to measure, because the health of the tree is very subjective. You can't just walk up to a tree and say, this tree is healthy, this tree is not healthy. You need to actually have numbers for your dependent variable, and a number I thought of is, why don't we measure the weight of the fruit to determine how healthy the tree is. So that's how you would pick your dependent variable. That's all I have for you today. I hope you enjoyed the video, and I hope you enjoyed that sample experiment I came up with. Maybe if you even live on a farm, you could conduct that experiment. I don't know. But I hope it was helpful in helping you understand what the experimental design process looks like. If you enjoyed the video, I'd really appreciate it if you hit the like button and subscribe button. Hit the notification bell, and also share it using our Facebook, Twitter, and Instagram. You can find all of them in the description box below. Additionally, if you have any kind of advice for me, because I'm just starting this biology course off, please put it in the comments down below, and I'll try to implement it as I go on. I also want to hear if this is helping you guys, if making this course is really beneficial to you all, because AJ and I wanted to expand the science sector of eCoreAcademy. Additionally, if you want to voice those suggestions, comments, concerns, appreciation, whatever you want, you can always email us at eCoreAcademy@gmail.com. Also available in the description box. We'd love to chat with all of you. Lastly, we have a website up, so please check that out. It has a bunch of special features that the YouTube does not supply, such as notes, quizzes, etc. All these videos organized into comprehensive courses. So I implore you guys to check that out. Again, that's all I have for you today. Please look out for my next biology video, and I'll see you next time. Bye!